a quick outline of the work that we have done so far. So we started selecting some microwave SST from the AMSR-2 passive microwave sensor on board the GCOM-W satellite. We have ingested these SST into the operational near-time processing chains for the Baltic Sea. And finally, we have validated the output level 4 with in situ SST. Our plan is to repeat soon the same assessment for also for the Mediterranean Sea. So the motivation behind this work is that the two aforementioned SST products are at the present day are derived by means of an optimal interpolation algorithm that ingests satellite SST data coming from several infrared satellite sensors. And of course, as probably most of you know, the satellite SST retrieval from infrared sensors has the advantage to provide estimation of SST with high spatial resolution as well as high accuracy. But these kind of sensors cannot see through clouds, and this leads to data gaps into the level 3S SST, especially in areas characterized by persistent cloud coverage, which in turn may lead to a decrease of accuracy into the level 4 SST. On the other hand, passive microwave sensors, they can see through clouds, thus they have the potential of increasing the satellite coverage of the level 3S products. So for our assessment, we have identified two different AMSR-2 SST products produced by JAXA and RSS. These are level 3 collated grease formatted products with a spatial resolution of 0.25 degrees. We retained only the highest quality SST values estimated during nighttime overpasses of the satellites of AMSR-2, because that's what it's done in the current operational chains for the two products. We choose the best AMSR-2 product by doing, between these two, of course, by doing an intercomparison against reprocessed and in situ SST. And by best product, of course, we mean the product with best accuracy and best observational coverage. These are the results for the intercomparison with reprocessed level 4 SST for the Baltic. We have in the red box the JAXA product, and in the blue box the RSS product. And going from the left to the right, we have the spatial and temporal AMSR-2 observation coverage, the spatial distribution of mean bias, standard deviation, and finally the root mean square difference. As you can see, the JAXA product has a higher number of observations, with a total number during the 2 years that we took into account in our analysis, which is almost double the one from RSS, and it also has a smaller standard deviation. The same kind of intercomparison for the Mediterranean Sea tell more or less the same story. We see as well in this basin that we have more observation for the contained, let's say, in the JAXA product. This time the mean bias is of a comparable order of magnitude, but probably we have to, it is worth mentioning that in the operational chains, all the SST observations are bias adjusted, so this is not a, let's say, a major selection criteria. Okay, these are the monthly time series of the same metrics we have seen in the previous slide. The red plot is for JAXA, and the blue plot is for RSS, Baltic on the left and Mediterranean on the right. This is just another confirmation showing the superior coverage and accuracy of JAXA compared to RSS. We also repeated this intercomparison by using a subset of observations that are in common between the two datasets, between the two products, and we obtained more or less the same results. This indicates that the two products do differ actually, and that the difference is not related to the different number of observations between the two datasets. Okay, we move on with the intercomparison with in situ data. In the box, there is the dataset we used for the validation dataset from MEMT from which we took SST values from these the instruments that you can see, Argo drifters, mooring, and ships. And these are the results for, in particular, for the drifters for both the basins. So probably at this time you are convinced enough that the JAXA product has a high accuracy and special coverage of the observation. I've also reported in the two tables on the bottom of the slide the overall values, and I have made bold the values for the let's say for the winner product, which I finally reveal to you was the JAXA one. These are the same results for the other instruments. So also the Argo mooring ships for the two basins, but probably we can move on to the next slide. So finally, once we have selected which kind of product to use for the AMSR-2 we made so far several test runs testing different ways, different methods of ingesting the microwave SST into the operational chain for the Baltic. We have started with a base run that is, let's say, business as usual. I mean, it only ingests the infrared SST. And then we started increasing we started including passive microwave SSTs, and from one test run to another, we basically augmented the number of observations included. Okay, these are some graphical examples that I think will explain better what we did. Okay, these are some level 3S SST coming from some of the test runs I've listed in the previous slide. If you look, for example, at the top left SST, this one contains only infrared observations. So you see a lot of gaps in the data caused by the cloud coverage. On the top right, we have another test run in which we have included the AMSR-2 observations as well as infrared. So you can see that most of the data gaps are starting to get filled with information, with observations. In particular, in this kind of test runs, we have included the same AMSR-2 SST into the closest grid point in the interpolation grid, but also in all the grid points that are within a 5-kilometer radius around. On the bottom left, you can see even higher coverage because we have tried ingested even more satellite AMSR-2 observations. And the last example on the bottom right of the slide is an example. Is a test run that we made in which we have subsampled the AMSR-2 SST prior the ingestion together with the infrared. These two figures are just an example of how the how the observations coverage increase when we add the microwave observations together with the infrared. I forgot to mention before that we have studied a period of 2 years. So you can see that for these two test runs, we have, for example, in the North Sea, at least 450 days more during these 2 years covered with microwaves observations, while for the Baltic, we are at about maybe 200 of days more with observations. Okay, these are the results of the validation with the in situ data, in situ SST of both the level 3S and the level 4 of the test runs that we made. Okay, starting from the top, we have the mean bias going down. We have the standard deviation and the root mean square differences. On the x-axis, we have all the different test runs that we made. On the very left, we started from the infrared, so the test run that is just only infrared, of course. And the different colors are for the different instruments. I hope the legend is big enough, but blue is for Argo, orange is for Drifter, and green is for mirroring. So basically, what do we see here? The main trend is that the inclusion of microwave observations, the more microwave observations we include into the optimal interpolation algorithm, the larger the standard deviation and the root mean square difference became. And there's a difference in particular between level 3S and level 4. That is, for the level 4, if we once we have started including microwave observations, we have so a modest decrease in the standard deviation and the root mean square difference. But when we ingest more AMSR-2 they are still increasing anyway. Unless we start we do the subsampling test run, in which we have still a diminution of the values, but comparable of the one of the second test run we made. Okay, I will skip this one. This is a first verification we made about the geographical position of the matchups, and as you can see, the two basins are not covered in a uniform way by the different. For this, in this slide, we can see on the left the Drifter and on the right the Argo location. So as you can see, probably the validation results that we have obtained are somehow affected by the geographical distributions of the in situ instruments. Okay, this is the last slide. So some conclusions. We are in the process of doing an assessment of the statistical significance of the inclusion of this passive microwave into the Baltic and as well as the Mediterranean Sea product. We are still doing some analysis. Another future works that we are going to do is to assess the effective spatial resolution of the merged infrared plus microwave SSTs by doing some spectral analysis. For the Mediterranean, for now, we also made preparatory work for CIMAR that assessed the impact of this future sensor on the level 4 analysis for the SST into this product. Okay, that's it from my side. Thanks for your attention. I'm welcome to hear your feedbacks, comments, compliance, and everything.
Thank you, Mattia. Yeah, we'll go to the next speaker. is Peter Cornillon, and he will give us a talk about improved MODIS Aqua L2SST dataset with AMSR-E orbital matchups and global gradient fields.
Go over to the first slide. Huh? I don't know. I can start. I'm going to be talking about a data set, the R19 MODIS data set that's put out by NASA. And I start with the level 2 data. This doesn't count in my time, does it?
Press the button.
And I want, and so I've spent the last 4 years trying to get the data set so that I can use it for the sorts of things in which I'm interested. I acknowledge on the first slide, I acknowledge my co-authors, Ji Shen, who helped me an enormous amount setting up stuff at AWS, Amazon Web Services, as well as my buddy Chat. She and I did a lot of work with MATLAB, Python, Bash, and AWS. And so that's my introductory slide. So the reason, so it's still not my time, right?
I stopped.
Oh, there we are. We're getting close. Oh, you can't see it here. Oh, that makes it easy. So can we go back? Go back. And can I control it with this? How did I exit? I'm out of control. Okay, so, right. So this is the, great. So this is, yeah, I've already gone through all of this. And in addition to acknowledging my two buddies, I acknowledge some funding from NASA. So why am I doing this? Well, there are two main drivers for what I tried to do here, which was to improve this data set, or as we would say in the United States, to make it greater again or something. I find the current NASA version of the MODIS SST, oh wait, let me start my watch now because we're really talking my time at this point. Right, so I find the MODIS R19 data set to be really difficult to use for the sorts of things in which I'm interested. So I've modified the two data sets, one for Terra and one for Aqua, to facilitate their use for the study of fronts and gradients in the ocean. I'm also interested in enhancing the spatial resolution of AMSR-E, which is the footprint size is about 45 by 65 kilometers, but it's sampled on a 10 by 10 kilometer grid, which suggests the possibility of a 10 by 10 kilometer product. And for years, I've wanted to do that, to deconvolve it. And the most likely approach, given that MODIS is on the same satellite, is to use MODIS. So I've included all of the AMSR-E data in with my files, my MODIS files. The two data sets that I use are the primary MODIS L2 SST data sets available in GHRSST format, and they're the R19 versions of the NASA data. These data sets were produced or processed by the Ocean Biology Processing Group at NASA Goddard Space Flight Center, and they used the University of Miami retrieval algorithm. Each of the Terra Aqua data sets consist of about 2.3 million 5-minute granules. They extend from the early 2000s to present. They have global coverage, approximately twice daily, clouds permitting, of course. and the spatial resolution is approximately 1 kilometer at nadir. AMSR-E, for AMSR-E, we used a version 7 of the AMSR-E dataset produced by remote sensing systems, which again is the 10-kilometer product. The data set consists of approximately 55,099 minute orbits from early 2002 to present, or mid 2002 to present. I'm sorry, not to present, to 2011. And it's got global coverage with a spatial resolution, as I already said, 45 by 65 kilometers and sampled every 10 kilometers. So the first part was to try to fix, the first part of this project was to try to fix the R19 data set. And I found 3 basic things that I wanted to address: the granularization of the data, the bow tie effect, and the quality mask. And I'll talk about each of those right now. For granularization, the problem is the data exists in 5-minute granules, of 5 minutes of satellite data granules. And these are really difficult to use, especially if you're interested in something that spans granules, or if you want to look at the globe, at the entire Earth. So my solution was to merge the granules into complete orbits, and the orbits started with a nadir pixel near a 79 south on the ascending portion of the orbit. And I chose this latitude because it was one that minimized the amount of water area that would need to be stitched between orbits. And it also turns out that it's the same place that AMSR-E starts their orbits approximately. It turns out that of all the parts that I did on this project, this one was by far the hardest. And that's because the data, the metadata associated with the granules was flawed in a lot of places. So it made stitching them together in orbits really difficult, which is one of the reasons, I guess, that I'd started doing it in the first place without even realizing that this was the problem. So this is what one orbit would look like, 20 granules approximately stitched together. And the thing that's cool about the data set is that the location, there are about 40,000 scan lines in the orbit. The latitude location of a given given scan line is about the same in all 100,000 orbits because they start in the same place and the satellite's always going around the same way. The second problem that I addressed was the bow tie effect. And so as the distance from nadir increases, the size and shape of pixels changes. The long scan size of a pixel increases substantially, but more importantly, the along track size of the pixel increases. It's only a small amount. And for a single detector sensor, that's not a problem. The pixels at the end of on the swath edge overlap a bit, but that's not a problem. They're spatial. Their spacing along track direction is about the same. For multi-detector scanners, this is a problem. The along scan properties remain the same, but the same is not true of the along track properties. MODIS uses 10 adjacent detectors, and 1/2 of a rotation with a mirror results in 10 scan lines. Scan lines from group 1, the first half of the mirror, will overlap scan lines of group 2, and they start the overlap about halfway from nadir to the swath edge. So I'm showing here a picture of what it looks like at the swath edge. And I used MATLAB to regrid the data. There was some messing around, but in the end, I have a new L2 grid, if you like. It's still in swath coordinates, but all the scan lines are now parallel effectively. The third thing that I addressed was the quality mask. The quality of each pixel is flagged from 0 to 5 based on a variety of characteristics or criteria by the University of Miami algorithm. One of the criteria is based on the satellite. One of the criteria is based on the difference between the retrieved SST and a reference SST. and they used a fixed 2 Kelvin difference. And if it was more than that, they flagged it as cloudy. And this resulted in a lot of pixels being flagged as cloudy in areas where things were changing rapidly. A second criteria is based on the range of brightness temperatures in a 3 by 3 pixel square. And this ended up cloud masking or masking a lot of pixels in high gradient areas. Both of these problems I've addressed in the improved version, although only a small fraction of the pixels are retrieved with these fixes. It turns out it's a large fraction of the pixels in areas where things are changing a lot, which is of interest if you're interested in gradients and fronts. So this shows an example image where, let me just check the time. Oh, good. This shows an example image where the gray are masked out pixels. The red band in the middle is the Gulf Stream, my favorite area. And the black pixels here shows pixels that were masked by the reference temperature, but my algorithm unmasked those. I believe that everything that's black here is actually good and was improperly masked. Here's the same for pixels that were masked because of the variability and the brightness temperature in 3 by 3 squares. And so this is, again, the original image, and then this is the unmasked version. So it's not a lot of pixels, but there are pixels where things are really interesting. So once I combined the granules into complete orbits and fixed them, as I just described, it was really straightforward to obtain the gradient of the field. So I used the Sobel gradient operator to obtain the eastward gradient, the northward gradient, and the gradient magnitude at each pixel location in the orbit. And so that's also one of the fields that's included in my output file. And then I added AMSR-E data to this. So I took the complete orbits of AMSR-E, wind speed, water vapor, and cloud liquid water. I didn't include rain, and I'll tell you why later if you want to know, but I didn't include it. And these were each added to the new MODIS files that I was producing. So now I have a complete fixed MODIS SST and all these AMSR-E parameters in the same file, fields in the same file. But these orbits are not in the same coordinate systems. MODIS is either cross-track or whisk Brom scanner is the blue line there, and AMSR-E, AMSR-E are the gray ellipses. So what I did then is I created a new coordinate system. So this is where I started. On the left is the MODIS. On the left is the fixed MODIS coordinate system and the fixed MODIS SST fields under that. On the right is the original AMSR-E coordinate system. I then created a 10 by 10 kilometer square in the same L2 coordinate system as the original MODIS data. So I averaged all the pixels in a 10 by 10 kilometer square and stepped away from nadir like that. And that's the little square under there. I then mapped all of the AMSR-E data to that new coordinate system. Remember, AMSR-E is sampled on a 10-kilometer grid, so that's why I chose to do it this way. Following that, oh, we're 2 minutes. You got to be kidding. It says 4 minutes here. So then I mapped the L2, my L2 equal area to the AMSR-E grid. Finally, I convolved those with the AMSR-E footprint. So if everything was perfect, the bottom one there, the convolved one, and the top one would be the same. That's the idea. All of these are included in the output file. Okay, and since, I'll go really fast here. All Aqua and Terra data through December 2024 have been processed. They were done with MATLAB. Cost about $2,500 to do Aqua at AWS and about $2,700 to do Terra. And these data are all available on my site, sst.ui.edu, although the Terra data is still being moved over, so it probably will be another week or something before it's over. Okay. So this says I still have 3 minutes to go. 2 minutes, okay. Okay, so I'll skip over. This is just shows the what this site would look like. I'll skip over the next part. Oh, this is where I asked my buddy ChatGPT. I wanted to ask her to do something, so sweetie, do this, but I'll skip all of this stuff. Yeah, we're skipping it. There is one slide here that I think is of interest. This shows the growth, the rate at which large language models are improving their capability of coding. And it's doubling, their capabilities of coding are doubling every 7 months for large language models. So the bottom line is, if you code and you're not using a large language model, you're behind the curve and soon you'll be obsolete. But the last part of my talk is on, stall a minute, is on the summary statistics from the gradients. So what I did is I averaged gradients by 1 degree square by month. So I took all this, my entire data set, I averaged the gradients that way, and you can read these things. I just want to show the last part. This is the mean gradients over the 22-year period from all of these data. And what I then did is I took the last 5 years and I averaged them and I subtracted from them the first 5 years, the mean gradients in those 2 periods. And this shows the difference. And you can see 2 areas or a number of areas where there are substantial differences. So what I did then is I went to those little squares and I averaged them times up, it says. Yeah, that's what it says here too. Actually, it says I have 45 seconds here, but so I averaged those. And what I really found startling was that in the area off of Peru, for example, the mean gradient has increased over this 20-year period by 15%. And it's increased by almost exactly the same amount in the Kuroshio. And if you demean it, they both have a periodic behavior which is almost identical with the Kuroshio following the Peru data. And if you look at one other area here, well, maybe, oh, I guess I get shut off, huh? Okay, I'll just go through the summary. Well, you can read the summary. I'm all done. 15.15 seconds. I'm sorry.
Thank you, Peter.
Yeah, who's next? Sorry?
We'll take questions
it's online.
later. Yeah, now
okay,
next talk is by Ed Armstrong on the optimization and performance of GRIS data in the cloud. It's an online talk. Ed, can you hear us?
Yeah, I can hear you. Can I go ahead and share my screen?
Yes, you can.
Okay, I'll get going here. Good morning, everybody.
Please go on.
And I'm sorry I'm not there in person. I really miss the face-to-face interactions. But unfortunately, this is the best I can do, is to present to you virtually. All right, so my talk is on the optimization and performance of GRIS data in the cloud. There you see my co-authors. You might recognize some of them. Myself, Dean Henze, and Celia Wu, we all work at the Jet Propulsion Laboratory, and Amy Barcia-Uskas, who had a nice poster on ice junk. She's from Development Seat. All right. Here we go. This will be the overview of my talk. I'm going to give you an introduction to the principles of cloud data optimization, talk about the different technology implementations, virtually czar and ice chunk, and then review the actual PODAC data implementations of some of these technologies. And a core part of my presentation is to show you some practical examples of accessing and computing with these new resources, and then wrap up with some future work. All right, so cloud data optimization through virtualization. What we're really after here is to build an ecosystem to improve the data access and the compute in the cloud. When I'm talking about the cloud, I'm really talking about AWS, where the NASA Earth Data Cloud, all the data, including the GHRSST data that we manage here at the PODAC, are located. And there's really 4 key points about this optimization strategy. One of them is to optimize the data structure. And that's essentially using these technologies. We don't reconfigure the original netcdf files, leave them in their native format, but we build an external JSON reference file. That's the virtualization part that contains all the chunking and the byte structure and really all the variable information for a particular granule in a particular data set. And for each data set, there's just one of these JSON reference files. The second part is the optimization of the data access to use open source libraries such as XArray and or ZAR to lazy load just the data subset in space and time. And I'll talk about a little bit more about what that means here in a second. And then to optimize the compute, so use traditional Python, NumPy, and or Dask to compute on those portions that you're interested in. And really to rinse and repeat all these steps for different data sets to make sure that is a well-defined workflow. So the little cartoon on the right-hand side just shows I'm just trying to change something here on my screen right here, so I'm blocking some of my text here. Okay, but you know, the first part shows how we traditionally operate with a file format. We're accessing the individual granules and maybe chunks in those granules, and really there is some overhead. I presented on this topic a little bit last year. For the software to figure out exactly where it goes, needs to go inside the file to fetch the information that it needed. And this overhead request is there every single file. And every time you reopen the file, you need to redo that. Versus with the optimization approach is that you have, in a way, pre-built knowledge of the structure of the file. You essentially just read and build that knowledge into memory only one time in a compute operation, and you really need to, then you have the information of where to go inside those individual netcdf granules to get the data of interest. So that's the difference, or one of the differences. All right. So we are leveraging in the PODAC this technology called VirtualiZar. This is the preferred Python library. It's a close cousin of something you might have heard called Kerchunk, but we use VirtualiZar. A couple reasons for that. They're both open source Python libraries that pre-process data files like these, the netcdf HDF, and create these lightweight external JSON reference files. And again, the lightweight reference files that map the internal byte locations of the data, in the case of VirtualiZar, to the ZAR data model. And again, we're not changing the underlying data under the hood. We're just creating references to it. VirtualiZar does use Kerchunk under the hood, but VirtualiZar, this is the key reason why we're kind of migrating to VirtualiZar, is that it has a robust open source community behind it. And so that's one of the primary reasons why we've focused on VirtualiZar versus Kerchunk. But at the end of the day, with regards to which technology you use, the end result is identical, essentially. Give me 1 second here. I'm having a little problems here on my screen right here that I'm looking at. I don't think, okay, yeah, there we go. Move that out of the way. And maybe you can see that, so move that out of the way. Yeah, go away there. Okay, next slide. Well, we've also looked at IceChunk. So hopefully you've seen the poster that Amy presented and learned a little bit about it. But this is the newest technology that's building on Kerchunk and VirtualiZar. It really it really operates like a kind of transactional database. You could think of it that way. It's still built on the ZAR data specification, but because of the way it's designed, it has a number of unique capabilities, including things like version control. We can go back in time to see a certain snapshot of the data. And then, therefore, it's more amenable for things like near real-time operations where you're like doing data appending, or you might have reprocess data that you are, a few days old that you are then appending to the time series. There's essentially kind of like locking, file read locking, so you don't overstep and say perhaps even overwrite while somebody is reading, so you see consistent snapshots, and therefore it really lends itself to kind of like parallel I/O operations. So we've leveraged the work of Development Seed. So this technology, I didn't say it, but it's been designed by this company, Earth Mover, and the NASA Impact program has funded a study of applying this technology to various NASA data sets, including some from the PODAC, as shown by Amy in her poster. All right, so as I mentioned, we've applied this virtually ZAR to several data sets. And so where do we stand in as of this month? So we have applied this to the ASTIA reprocessed SST time series. We've also applied it to MUIR 1 kilometer, but only the first 10 years, and then MUIR 2.5 and AVHOR. I'm misspeaking a little bit because some of those are not publicly available yet, although we're on the cusp of releasing those. We've also done a virtual data sets for the CCMP ocean winds, Oscar ocean currents, and SMAP salinity, and there's little links there that actually take you to the landing pages. The dataset JSON file is available in a public S3 bucket, accessible from the dataset landing page, as I'll show. And they're currently tagged as experimental. And we're also going to be making available this ice chunk version of the MUIR 1 kilometer that Amy demonstrated in her poster, but we haven't give us another week or two to get around to doing that. Okay, so this just shows an example location in the website of where you would find this. This is the ASTIA here. So if you go to the data access tab in the dataset landing page, you'll come to this little box right here. This is the new part here where you'll see these references to the different virtual data sets. And we've done for JSON, and we're also experimenting with Parquet, which is another file format for ASCII data, perhaps a little higher performing than JSON. And so if you click on one of those, what you actually see is the ZAR representation of the ASTIA data set that has all the information, the byte locations, the byte offsets, the chunking, all the information a program needs to open the data set and access just the information that the user wants. So how do you do that? So I'm going to show a little example application of interdisciplinary 10-year time series analysis where we open the CCMP 6-hourly ocean wind data set and the ASTIA reprocessed SST data set. So each of those are pretty large data sets. CCMP is just under a terabyte. And ASTIA is 11 terabytes. So we're going to open these reference files, and we're going to be using the Xarray Python package to do that because it has a lot of nice user-friendly features that I'll just talk about here in a second. Open them as Xarray data sets. We're going to subset in space and time, and this is what we call the lazy loading in a regional 1-degree box over the all times in this particular time series. Calculate a regional spatial mean, and then resample those means to a common time interval. And we're going to pick 1 month, and then we're going to plot it. Okay, and so where are we going to do this? We're going to do this in the Gulf of Tehuantepec, and so this is a very interesting oceanographic region. At certain times of day, we see a little snapshot of this region here, and so this is interesting from the perspective of this interplay between winds and the ocean SST. Where in the wintertime, you have a strong winds that blow through these very narrow gap regions here between the Gulf of Mexico and the Pacific Ocean. This is the Gulf of Tehuantepec. And so, yeah, of course, when we have these strong winds, we get open ocean upblowing. And so in this case, we see in this little 1-degree thumbnail, the response of the ocean sea surface to the winds blowing and the decrease in temperature as cooler water gets upwelled to the surface. And so the plot, of course, you see there, the blue is the SST. I actually only did this for this particular run over the 10 years, the first 10 years of the data set, starting in 93 of the CCMP data set, 2002. The ocean temperature is in blue. and the wind is in red. And you see this very strong anti-correlative signal when the wind is high on the order of 10 meters per second. That's about 20 knots. The ocean temperature really drops. So it's kind of a cool demonstration of an interdisciplinary application of using these very long time series record to do something quick and dirty and very efficiently in both cost and time. So how long did it take to do this plot? Well, actually, I started up a more of a performance EC2 and EWS, that's 32 CPUs, and it took 6 minutes end to end. But when you think about what I did, that I crunched through a multi-terabyte time series, and I did some significant averaging and resampling, that's a pretty fast result. If I downscale my EC2 to something a little bit more modest, that has 8 CPUs, that takes 10 minutes. And in the first case, if I apply some parallel processing via Dask, I can cut it from 6 minutes down to 2. So yeah, what are some of the costs of this? Yeah, not very much. I mean, the performance EC2 is something like about $5 an hour. The modest one is like, $1 an hour. So these are not expensive operations in terms of cost. Continue on. So yeah, I just wanted to demonstrate some, the functional code snippets to do that. It's really quite simple. I use this Earth Access package, which is a nice package developed by NASA to streamline the access to data in the NASA Earth Data Cloud. So there's a login method where I just pass in my username that does all the authentication. I establish an S3 file system in the next step. And then the third step is actually reading the data with XRA. And there's a little wrapper that's built around the XRA open data set. But we're just essentially passing that JSON URL that you saw previously on the Ostia homepage there, and it opens up in just a few seconds. You see the size of it is of the data set is 11 terabytes right here. It only took less than 10 seconds to open it. This line here actually does the core computation. I just kind of condensed everything into one line to do the whole thing, to do the lazy loading, the time slicing of the long and lat ranges to that 1 degree box over the 10-year time series, and calculate the spatial means, and then resample those means to 1 month. So that's the part that took like nearly 6 minutes. But the efficiency of the code here, of what you need to do to actually get the data, really straightforward and really quite simple once you learn this. Okay, here's another example of calculating the long-term spatial mean just for January. January is that peak month where we see the big uplink signature. In this case, I do it over the entire 40-year plus record of Ostia. And again, it's a very straightforward process to do this. I just basically do the lazy loading here. I select just the January time steps from the time series, and then I calculate the mean, and that took only 30 seconds on one of those modest AWS EC2s with 10 CPUs. So very efficient, very quickly. When you think about the cost of this, it cost me maybe about 5 cents to do this. All right, I'll just wrap up with some future work here. We've created some of these reference files, kind of through hand curation, so to speak. But we're strategizing now how to kind of harden this and design a workflow. And we're looking at these technologies like Apache Airflow and different AWS services. So the idea here is that we want to, at the end of the day, be able to keep these reference files for really all gridded data sets and other PODAC data sets that we curate, and that, of course, all the different physical parameters we support, including ocean salinity, winds, and currents. So what I've been talking about here is specifically working in the cloud. So you're accessing the S3 links. But one of the things we're looking at is how to create these files with the HTTPS links. So you don't necessarily need to be in the cloud, but you can access and run this outside the cloud. Of course, you'll be able to perform these operations, but there will be some cost, of course, of bringing over the data over the wire to your local system. That'll increase the time of the operations compared to working natively in the cloud. But yeah, there's a lot of users out there that still want to operate in that manner. where you just access the data via HTTPS and then bring it locally and then do your things. But you can still do the subsetting that I just demonstrated. It'll just be taking a lot longer, or taking longer. We're going to continue to investigate and implement the ICE chunk for additional GHRSST data sets and related technologies. That's an ongoing effort. But a lot of this stuff is evolving very rapidly. And so one of the goals is we need to provide the user with, not only the most choices, but also and pathways, but also provide them a stable environment. Because we don't want to frustrate the user of, trying to access one of these virtualized data sets and dealing with, things like dependencies and the different Python libraries breaking the workflow. So we need to be cognizant of that. Another goal is we want to investigate the application of these technologies to level 2 data and beyond. But again, we're here to help you on your cloud journeys, and see our cookbook tutorial on using Virtually Czar. Actually, that's the implementation part. And we'll also have some additional recipes for the reading part, such as I've demonstrated right now. All right, I think I'll wrap up right there. Thank you very much.
Thank you, Ed. Quite interesting and important to improve how we're accessing data. I think Peter also showed how much effort he put to access the data to do some analysis. We have to improve it, definitely. So let's now start with the questions. We go backwards. So if some questions first for Ed. Yes.
So Dave Letty here. Does NetCDF4 compression or things like H5 remap, does that break your JSON files? Presumably offsets would change when those kinds of file size reduction processes are implemented.
Yeah, there's a key requirement. I didn't say that there has to be consistent chunking across the entire time series, including things like compression. So if it is a little bit ad hoc, this approach will work, where it'll need a lot more hand curation. You can get it to do it, but to actually build the reference file takes much more time and effort. So yeah, it is a key requirement that the time series you want to build these reference files on should be internally consistent with regards to variables, with regards to how those variables are chunked, and to the compression schemes that they use. I'll say a little bit more about that at the GDS3 breakout, where I'll kind of dive a little bit deeper into kind of what's going on behind the scenes here. But thanks for that question, David.
Thank you.
Hopefully I answered it.
Do we have some other questions online? Okay, second.
See, Jorge has his hand up.
Yeah, Jorge, please go on.
Oh, I'm sorry. This was a question actually for Peter. If that's okay.
Maybe just quick to see if there are some other questions for Ed.
Okay.
Yeah.
Hello. What is the accuracy of your CCMP print?
Oh, good question. What is the accuracy of CCMP? I don't know the answer to that offhand. I'm not an expert in the product, but I would say at least plus or minus a meter per second.
Okay, thank you.
So yeah, it's a fusion product across a number of different ocean wind remote sensing platforms, including things like QuickSCAD and AMSR and stuff like that.
Any further questions? Maybe we can then continue with thanks, Ed. I think tomorrow we'll have discussion on this, and also we have the discussion on GHRSST priority, so we can also address it. So maybe last question for Peter. Jorge?
Oh, thank you, Peter. Just a quick question. You mentioned that the data is available. We can get that from University of Rhode Island directly.
I'm sorry, I'm having a little trouble hearing you. I guess up front it doesn't sound quite as good as it does further back. Repeat your question.
Okay, no, Peter. Hi, this is Jorge. I just
Yep.
wanted to confirm that you mentioned that the data you reprocess MODIS is available through the University of Rhode Island. We can access it directly.
Yes. Yes. So the data I produced is available on my network attached storage devices. I have Synology devices running OpenDAP servers. The data I used was from the PODAC in the cloud.
Okay.
And so that's why I processed it at AWS. So those were the level 2 data I started with. I actually merged those also with data from the Ocean Biology Processing Group for a number of complicated reasons. But yeah.
Okay. All right. Thank you.
Any other questions to Peter?
Hey, Peter, smart one from Orbital. You've mentioned 3 big problems with the MODIS data. I would have assumed that the user community interested in France is mostly preoccupied with the amount of striping on MODIS data. Have you done anything about it?
Can you repeat it? I'm having a little trouble hearing you also.
The biggest problem, I think, for the user community working with France and working with MODIS data is stripe noise. Have you done anything about it?
Is what noise?
Stripe noise.
Stripe noise. No, I didn't do anything with stripe noise. That's a problem, but I don't think that was the biggest problem.
Well,
the biggest problem from my perspective was that a lot of the major fronts were masked out, which is what I showed, and those I fixed.
the reason why I'm commenting on this is back in 2014, I conducted an experiment where I plotted 2-time series of SST gradient magnitudes for 20 years.
Mhm.
And I used 2 products. One was the original one, and the other was the destriped one. The original one showed a very positive trend, just like the one that you showed, and the destriped one canceled completely the trend.
So when you talk about calculating the gradient on the original data, you had done some modification to it to deal with the bow tie effect, right?
Bow tie effect and striping are 2 different things.
I understand that. Well, they're sort of different. They're different because of the detectors. I understand that, but you have to essentially deal with the bow tie effect if you want to calculate the gradients from the original field, right?
Sure. But you
Okay.
also need to, in addition to that, remove the stripe noise.
It will help, but the biggest problem I had was from the bow tie. And why did you say that it increases with time?
Because the detectors on boards, the MODIS instrument, any instrument are going to degrade over time.
Okay, actually, in the slide, I didn't show at the end because I accidentally skipped over it. I looked at another region in the equatorial Pacific, and there was a decrease that was almost identical to the increase over the same period. So I don't think that the increase that I was seeing had anything to do with the degradation of the sensor. Remember, I only looked at it at 2 or 3 different places where there was a very large increase. The whole rest of the field either was small changes or even decreases. So I think if I did average at in the subtropical region, and it turned out it was almost perfectly flat. So I don't think that's certainly not what caused the problem off of Peru or in the Curacao, because in the eastern equatorial Pacific, I see exactly the opposite, it's really intriguing. I have no idea what's doing it. I got all those results yesterday when I was messing around with the data. For 4 years, I've been trying to make the data set usable, and now I can use it, and it's really exciting.
We have an online question from Ed, please.
Hey, Pete. Yeah. Hi, Peter. It's Ed. I just wanted to quickly, if you could comment on how you're using the large language models to do program. And I'm kind of interested, like the complexity of program you're asking it to do. Could you maybe describe, like, you know, how are you using it? And are you asking it to like write hundreds of lines of code or like just a subroutine? I'm kind of curious, you know, because I've, of course, experimented with as well as many people are, as you're alluding to. Yeah, if you're not using it, you're kind of falling behind. But just curious about how the complexity of programming problems you're giving it. Could you comment on that?
Yeah, the problems I'm using it for are short. And in fact, that curve that I showed, which was a paper that was done by a group at Cisco, where they looked at the doubling time, what they defined as success was if the large language model was correct 50% of the time that it wrote the code, and then they compared that to how long it took a human to write the same code. And in 2019, it was about 2 seconds. In 2025, it's about 1 hour. So the amount of time that it would take you to write code in 1 hour, it will write correctly about 50% of the time. And they predict that by 2030, it'll be 1 month. The example that I showed, that I was going to show, but I skipped over, what might be of real interest to you, what I did is I went in and I captured the DMR, or it could be the dump from a netcdf file. I put that into ChatGPT, and then I said to ChatGPT, go and get all the data between 20 north and 40 north and return these 3 fields. And it actually figured out that it could read another variable in the data set to determine the 20 to 30 north part, 20 to 40 north part, and then to do the extraction. And on top of that, it actually produced a plot of the data, and it did it correctly right out of the box. I can certainly envision in the future, within a year, you'll go to your users will go to a large language model and say, get me these data, and all the interfaces that you now have to find data and extract data, it'll do it all for them. And I think that's very, very close.
I know I've experimented with that myself with things like ChatGPT, and in many ways it can do tasks like that already, or get very close, or at least point you to the resources and how to use them. So yeah, well, thanks for those the plot and the talk. Thank you very much.
Mm-hmm.
Thank you. Let's move for questions for Mattia. Is there any question? Jean-Francois?
Yes, thank you. Yes, I have a question about your comparison between JAXA and remote sensing system products. So you showed like statistics, but like overall statistics over your region of interest. But for instance, on some pictures, we could see that there was a very serious bias along the coast, which is a non-issue with AMSR data. So did you also compare the 2 products with respect non-issues like along the coast, over rainy areas, or with RFI? If the quality of the flag is also different, and how it compares, because I think if you put badly flagged data in your analysis where you don't have other cloud cover any other data, it can have also some RST effect.
Sorry, I have some problem listening at you. Can I ask you please to talk up a bit louder?
So in your comparison between JAXA and RSS products, so you have shown global statistics based on in situ data, but in some areas like along the coast, you could see that there were a very strong bias, for instance, because of the land contamination. So did you also compare the 2 products with respect to the flagging of this bad data, whether if they are too close to the land, or if it's rain contaminated or RFI contaminated?
No, so no. Basically, what we did was simply take all the. We made a selection based on the quality level. So so if I got your question right, we took only the quality level 5 SST, and we did a comparison between these 2 kind of SST.
So you don't know which quality level, for instance, is best for.
Sorry.
Okay.
Maybe. No, I'm sorry. The volume. I can't hear properly.
Yeah. No, I was you didn't compare.
I'm here. I'm not running away.
So you didn't compare just to five actually one is better.
No, we simply took the quality level 5 for both the product and made the comparison.
Any other questions for Mattia? We can be a bit late with but online. Okay, maybe then we can close this part and let's applause to speakers. So we are starting now with a discussion on GRIS priorities, covering this session on advanced CC computing, retrievals and products. So we have a couple of, let's say, different topics here. One is more on the evolution of the algorithms, on cloud detection algorithms from Christina. Then we have new missions, NG, Sentinel-3 NG, and ACLSTR. Then we have several talks on the microwave, which is bringing importance to the microwave SST retrievals for the community. And then last was on the how to access data, and I think also Peter addressed also point on the using the LLMs for in the future, but more really how to improve data access for GRIS data in the cloud. So maybe let's start first with cloud detections and maybe related to Christina and some improvements in the algorithm. Any comments? Is there online? Simon?
Hi there. So I've been trying to follow along online as best as I can. This isn't actually about cloud products, but I've got to leave in a second. So I wanted to make it about data formats and things. So if I may, I'd like to say it would be really useful to have GRST input in the formats for level 1 data in the future, as well as the GRST output products. Also what the data producers, etc., would need in terms of the level 1 data that goes into the products. So perhaps that could be a potential priority for GRST, both for S3 NGO and other missions, just to hear what all the data producers would like in terms of the level 1 data, what formats, cloud compatibility, all that kind of thing.
Okay. Thank you. Yes, it's very important. We are already a bit late, I would say, but we have to catch up and give recommendation to community and basically for producer. Jorge, do you have a question? Comment?
Yeah, just one quick comment. I think the issue of the cloud masking also is directly related to the issue of applications in coastal regions, and I think that's something that we also need to focus on how we're going to improve access to the user community for these great new products, and especially the improvement in the cloud masking and the application in coastal regions.
Thank you. Ed?
Yeah, a quick comment here of what we need to be cognizant of the future is regardless of the pathways we decide to go on with regards to the formats, we need to be cognizant and make our data play very nicely in this growing ecosystem of services. Specifically with things like we need to be sure that our products that we build can be transformed to other products, right, that might be of interest to the community. So, say we don't produce a cloud optimized GeoTIFF, we should make sure that our data can be transformed very easily into cloud optimized GeoTIFF, because some communities like to use that. And as these new virtualized formats like ZAR, become grow in use in the community as well, we need to be cognizant of that as well. And I think this cloud virtualized technology that I talked about in my talk is one of those pathways to meeting that emerging new requirement. So that's another comment I wanted. We need to be cognizant of services, transformations, and being able to get the data into the user's hands the way they want to use it. Thank you.
Thank you. Chris?
So this is on the cloud question. I agree with what Jorge says about the coastal zones and cloud detection being a problem there. But it's generally in the infrared a problem in the open ocean too. If you look at L2P and L3 products, you see features you know are not oceanographic quite readily in even the best GHRSST products. And it's really nice to have seen a radically different approach being tried in this meeting, which I think is what we need, because obviously many approaches have been tried and we have yet to crack this problem fully. And it's important to crack it in the context of the fact that I've certainly had experience of those artifacts in data preventing the effective use of machine learning to learn other things about the features of the SST, because there was so much contamination from cloud that it was, obscuring what I was actually trying to look at. So it clearly is important, as that sort of application will increase in future as well. I have a second thing on a different topic, but related, if that's all right.
Yeah.
It's related to both the SIMR and the ASLSTR talks, where in the SIMR talk, we saw that they're doing an integrated retrieval of SST and wind and liquid water path and so on. And you've got to do that in the microwave because the emissivity is so variable with wind that you have no other choice. We get away without doing that sort of thing in the infrared. But with Paolo's combined instrument products, perhaps we should be thinking about more integrated retrievals with other communities, such as the cloud community and aerosol and water vapor communities too, because some of our problems might disappear if we're estimating all of those parameters together rather than separately. Just throw that one out as a consideration, and maybe ESA will help us explore that at some point.
Thank you. You have some comment, Paolo, on this? Okay.
Yeah, I wanted to.
Sorry, just.
Oh.
Yes, thanks, Chris, for this comment, and I really welcome your suggestion, because really so far there has been a majority of use of using the ASLSTR information, especially on aerosols, of course, to feed into the AOLCI processing. But I really like, your suggestion that we should also look at the other way, how we can use the data from the visible and near infrared push broom sensor AOLCI to feed into the SDR. So it is well received, and we will think about that.
Thank you. Masha?
To follow on with what Ed and some others have talked about with the cloud data, another part of this is access. And I've talked to a lot of people who have talked about how, there's a lot of barriers in terms of authentication that you have to go through. And some of those things require us to download data rather than being able to stream them, which is allowed by like optimized formats. We can't really get to the potential of these optimized data formats if we actually have to download the data. So I know I really urge agencies to think about making it possible to openly access the data, or to do it at least programmatically from like Python or something, so that you don't have to go in and download. But for each of us, because we don't have any control over agencies, we can store our data products in places like Radiant Earth does storage and things like that. So if you have a choice of where you can store your data products that does allow you to programmatically access the data, you're gonna also make enable cloud and other people's workflows to be more optimized.
Thank you. Dave?
Dave Wethy, South Carolina. So related to Tasha's comment, a lot of the reason for using the cloud is to not have to download data and move data from one place to another. And this raises the whole question about if one's trying to use both EUMETSAT data and data from say the NASA cloud, or say data from JAXA, or data from the Indian MOSDAC, even having just programmatic access doesn't really solve the problem, because you're still having to transmit data across long distances between different clouds that are in different silos. And there has to be some kind of solution to this that allows direct access without having to move files back and forth. And that's something I think long-term is going to be an issue, because each of these groups, EUMETSAT, the Indian Space Agency, JAXA, NASA, NOAA, they're all producing data in different silos. And somehow there has to be a way for the access to be effectively machine to machine between those silos.
This is a valid point. Also comments from my side. So one thing is first interoperability between the clouds. So we have different cloud providers around, and then even for you end users, it's very problematic if they want to use data that are not in the same cloud. And then what we need to achieve is basically that we have the processing environment close to the data, and not basically downloading the data, or even the connecting and downloading data, although not downloaded, is still retrieved locally. So we have to avoid this, definitely. But I don't know, this is definitely discussion on the agency, but maybe to have kind of layer in between what we did with the GRIS catalog, to have way to access directly data, regardless where they are, so using OpenSearch and so on. But then question is still really where to process the data. But this is driven by applications, I would say. Yeah. Any other comments, Peter?
Yeah, I was gonna quickly comment on that, if I may.
Ed, sorry.
Yeah, I mean, the cloud interoperability, it's a very difficult thing to solve and stuff. And it's something we're going to have to deal with, our user communities have to deal with for a long time, I think. But I think one of the ways, at least to mitigate against that, is this presentation I just gave with the example of lazy loading. So you're not downloading like entire granules, or like you're just moving the data that you're interested in working on, right? So you're just subsetting in space and time that information you want, and you're consistently doing that across the entire time series if it's virtually optimized and virtually czar ice chunk. That would be one method to reduce the volume that needs to kind of go down the wire between different clouds. But yeah, the cloud-to-cloud interoperability between AWS and Microsoft and Google Cloud, that will still be an issue, I think, that be around for a while.
Okay, thank you. Maybe last one comment. We are already late. Peter?
Yeah, and in my case, I went to the cloud to process the data because the data were near the processing capabilities, but then I had to pay to download everything I produced, and I produced 75 terabytes of data. University of Rhode Island actually covered the cost for me, but it wasn't inconsequential.
Okay, I think we covered a lot of topics. We can close now also this session. We'll have continued discussion tomorrow in the morning with Jeff is leading on this. So yes, we close now the session. Thank you.
Okay, and then for those who have posters, at least in the other room, we took them down because the poster people came and they're taking down the board. So your posters are on the side in the small room, and if you have posters in here, please take them down now. So, and if you are staying for the high latitude meeting, please stay in the room. We'll use the same link here, but we have to be out of here at 5 to 6. So let's try to be efficient.
By the way, guys, I have some excess beers from yesterday. So if anybody wants, they are over by Wipke. Grab a beer on your way out. I don't want to bring them home.